All right. We love the announcements the week after an exam because there just aren't too many of them. So now that the exam is behind us, thankfully, we have a good 3 weeks before we do it again. So nothing immediately on the horizon except for homework 2 due Wednesday. Expect homework 3 to be pushing out in the next couple of days, due next Wednesday. And I think that's just about everything. Anyone have questions about schedule? All right, it's been a whole 5 days since we talked about anything on these slides. We introduced the concept of context-free grammars as kind of the grammar that I introduced to you at the very beginning of the class. And then we learned about regular grammars. And now we're back to having what seems like full control over our grammars again without those annoying restrictions. So last we talked, we found a grammar for this language. Looks something like this, where we could split this down into, are there more A's than B's or are there more B's than A's? And the first S production was saying either there are going to be more A's than B's or more B's than A's, which we know right off the bat, thankfully. Great. We just go down whichever one happens to be true. And then with the S1 production, we can produce an arbitrary number of A's and B's. And then with A or B, we produce only A's or only B's, but we force at least one of them. And that becomes the way to produce the more A's than B's. Were there any questions on that example from a while ago, or do we feel like we remember it? And it's going well? Anything to cover, catch back up on? I still don't know what that was. But now we're going to answer another kind of question, which is looking at a grammar determining the language that it accepts. So here it is. Let's start by asking, what are some strings that this language can derive? That was crazy. I heard the shock by putting my arm on the board to not shock myself harder, and it shocked it so hard that it turned off the. Anyway, things that happen on Monday mornings. Some derive strings.
AAA, BBB.
Okay, yeah, that'll do it. AAABBB can be derived via something like S arrow ASB arrow AASBB arrow AAASBBB arrow AAABBB with the S going to lambda there.
ABB.
ABAB can be derived. Interesting. This isn't really something we've seen before. So if we do S arrow SS, we take the first S, we turn that into an ASB. Then it goes to lambda. We take the second S, and that becomes an ASB. And then it becomes lambda. That could produce AB, AB. What else? I kind of have a slant going with my handwriting. Any other strings that we can think of that are in this language?
I mean, if we want to be basic, AB.
Yep, AB. Quite a few others. So what's the language? If we had to describe that in some way, shape, or form.
The two things I've figured out is it always ends with A and B, and there's always an even number of A's and B's.
Okay. So the same number of A's and B's, yes.
Yeah.
Does it always end with AB? With the BB example up above ends with the first string.
Well, starts with A, ends with B is what I
Gotcha. It starts with an A, ends with
yeah.
B. Yes. Yep. Anyone else with some insights?
You're wrong to want. I want to like describe it recursively, where I like self-reference
Yeah.
the language itself.
That actually is, that's an important distinction within this language itself, as it does actually have a recursive use. Anyone have that moment of brilliance? It's okay, I'll have it for you. This is the language of parentheses within mathematical expressions, where if you replaced A's with left parens and B's with right parens, you could produce any legal set of parentheses or curly braces. Why is that? Why does something that is this simple represent something that is potentially that complicated? Why does that work?
Because you can, like with parentheses, you can just have them nest inside each other as many times as you need, and then
Mhm.
sometimes also next to each other, which this allows.
Right. So this is saying there's a left parent and a right parent, and what's inside of it is some expression. And this is saying there is some expression followed by some other expression. And if you recursively ask for one or two of those, you can create any arbitrary mathematical expression out of just those two rules, or any nesting scope structure out of any of those two rules. That's really cool that that can be done so simply, but now we can start to see why these kinds of grammars are very nice for something that a compiler might need to be able to do, like determine whether there are associated curly braces that map to legal scopes. Something like this could answer that question. Are the curly braces in this program set up in a way that define scopes? So really cool. Let's talk about next idea, which is the concept of a leftmost or rightmost derivation. First thing we need to do within this is define the concept of an ambiguous grammar. So an ambiguous grammar is really just one that there is at least one string within the language that it accepts, where there are multiple possible paths through the grammar that generate that string. As an example, here's a grammar. Let's see if you can determine whether this grammar is ambiguous or not. So we only know how to prove something is ambiguous. So what you might be wanting to do here is try to find a string that has two different sequences of productions that produce that same string. Think about identify the string and then identify the production orders. this seems difficult, you're probably overcomplicating it, because order also matters. Even if you're using the same subsets of rules, just being able to apply one before the other is already bad. Yeah,
Pretty sure you could use just the letter B in two different ways, so you wrote the A means lambda. And then the B is a B and then and then lambda. I had this worked out, I raised my hand and I forgot how it worked out.
I can finish your statement if you want.
Yeah,
But then inversely, you can change the set of orders. So you can start with going down the B line. So you can do B equals B and lowercase b.
and
the
then the
lambda,
and
and then the A, yeah.
Yeah, that works. The example that I have here is for AAB, but that also would work as described. So this just tells you the number associating with the production that was applied to get there. So on the top, we apply production 1 to get AB, then production 2, which expands the A into AA capital A. With 3, we're gonna make the capital A go away. 4, change the B into capital BB. With 5, make the capital B go away. And the only thing that was different is we swapped 4, this 4 here, but there was ambiguity between which A and B to do. We just handle the 4 first before this sequence of 2, 5, 3 instead of 2, 3, 5 as before. So you can just swap the orders of things and you end up producing the same string, but the idea was there was a different path through the grammar to get there. Ambiguity can go away if we force some kind of order. If there is ambiguity, then you do this before that, then we do some actual way of determining the order of operations for these associated productions. So if we move from left to right, saying whatever non-terminal is leftmost, we always do that first. We call that a leftmost derivation. So here, when we have AB, where we have ambiguity between do we replace the A with something or the B with something, a leftmost derivation will always say replace the leftmost symbol first. So determine what happens to the A before you determine what happens to the B. Rightmost is exactly the opposite. You're going to take the rightmost non-terminal and do that first. So it really just tells you an order, given there are multiple non-terminals, which one should you attempt to replace first? We care about ambiguous grammars because lots of reasons within compilers, we can't have multiple ways to handle a particular statement. Otherwise, it leads to situations where the same line has two different meanings, or there are two different orders or ways in which to interpret a particular statement, which might lead to something different actually happening underneath the hood. So we'll explore that in quite a bit more detail in a bit. But for now, we will just continue to explore what do we do with a leftmost and rightmost derivation. They're quite useful. Here's another grammar for you to consider. Let's provide both a leftmost and rightmost derivation for this string. Go ahead and draw them out. I recommend doing this kind of like trees, where you would start with the non-terminal S, and then just start to, okay, S becomes a capital AB, so you would have something like S becomes, so you can either write it out like this, where you're just saying S becomes A, B becomes, let's do something with the A, let's go ahead and do it that way. We'll go into trees next. Here's what a leftmost derivation might look like. Check and make sure you have something like this. Go ahead and produce that rightmost one. Maybe you can check a rightmost derivation. It's funny how the B goes away in this example, because the A can produce it all. So it kind of acts like a puzzle where at each point you're at an internal node and you're trying to decide of wherever it is that I am, how does this rightmost symbol help to become the entirety of the rest of the string? Or does it go away and the other non-terminal can handle it all? You can see how there's a search in here, how it's not necessarily prescribed which path to take. But one other way to think about this is as a tree. Anyone have any questions on the leftmost or rightmost derivations? Yeah,
There are more than one answer that we get.
Yeah.
Mine's a little different, but I think it still works.
it gets to that same point and you're always replacing the leftmost or rightmost non-terminal. Yeah, sometimes there are both, and ambiguous grammars have multiple, even leftmost or rightmost derivations sometimes, and that's especially bad. So parse trees can also help you to see this. I think I've drawn it out like this once in this class before, but in general, you would have some kind of leftmost side that says A arrow, A, B, capital A, capital B, lowercase c. If that were the case, then you would expand this A into each of those symbols at one layer of a depth of a tree. So you can start with the start non-terminal and continue to expand from there until you have produced the associated string where a depth first search through that tree that you created would be able to reproduce the string. The idea is that internal nodes are all non-terminals and leaves are all terminals. And then, yeah, as mentioned, a depth first search of that tree will print the derived string. Does it make sense as to why or how that is? I got one nod and a bunch of blank stares. I don't know what that means.
That means, need an example.
Means we need an example. Excellent. Let's go do that. Using this grammar, let's construct a parse tree for this exact same string. So same grammar, same string. Let's make a parse tree. So we start with S. There's only one thing S can do, become A, capital B. So we're going to do that. A, capital B. This A is great. It's done. It's a terminal. But if we're doing a leftmost derivation, then this A must become B, capital B, B. So we're going to make that where did we go from here? What did we do in that leftmost derivation for this B? Does it become A or does it become lambda? Becomes A. What did this A become? The B, capital B, B again? Then what does this B do? Goes to lambda. What does this B do? Goes to lambda. So now all of the leaves of this tree are terminals, either the empty string or some character that has some meaning. And if we do a depth first search through this tree, we find A, B, 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 done. And if we printed that out as we did that depth first search, we would have the associated string that we were trying to find with this parse tree. Does that make sense? People see how that fits together and works? Show of thumbs, maybe? Since we're seemingly still on a Monday morning hangover. So note that this B expansion down here, all it did was produce two B's. And it doesn't matter whether that produces B's in between here or afterwards, it doesn't really matter because we have the associated, we could either have a BB followed by a BB structure, or we could have a BB with the BB in the middle. And when we have the ability to do this, we can put it in either place. So this could have become this B's expansion as easily as it was this B's expansion. If you just flip which one was done, this B becomes lambda instead. This B becomes A, which becomes B lambda B, which does exactly the same thing with respect to this particular string, which is again how we know this grammar is ambiguous. There are two different ways that we could produce this string. In fact, the example on the slide uses the other one. So exactly the same parse tree. It's not the same tree, but it produces the same string, which again is not quite ideal. So what's nice here, we can note that we know which production was used, but we can't really easily see the order in which they were done. If we had a leftmost derivation, we would have chosen to apply this before this. If we had a rightmost derivation, we could have chosen to apply this before this. But it would have generated the same tree as long as we chose the same productions left to right or right to left. Yeah.
So the way I was thinking about like leftmost derivation versus rightmost derivation is that you'd have to fully resolve the left thing to like. I would think that the way I was interpreting the rules was you would have to do that one where it's like the tree stack line to be on top of the other one. Is that right, or is this technically still leftmost derivation?
Well, this doesn't even state which one it is. It can be left or right, depending on if we did this, then this, then this, then this, then this, it would have been leftmost. And if we did this, then this, then this, then this, then this, it would have been rightmost.
You don't have to like, so like, the way I was thinking about it is if you can get the entire answer, just on the left one, then you should do that. But that was.
Okay.
That was kind of like my interpretation of it, but if this works, then my interpretation is wrong.
Yeah, it just depends on, this entire tree, would have become the other, I guess, with leftmost. Yeah, because then you would have, well, you still had an option when you did this B.
Yeah, I guess.
That became either an A or a lambda, depending on which you did. The only way to produce this would have been a particular way of a leftmost or a particular way of a rightmost derivation, but you could have done the others just as easily.
Much like in the example that we had done before, you basically, for the rightmost, you just basically instantly turn to the left.
Yeah.
So you're just like, that's not.
Yeah, we're not even gonna worry about that, see if there's a way to make it without it, which there was. Yeah, you're not wrong. So if we have left to right child recursion, we have leftmost. If we have right to left child recursion, we have rightmost. Any questions on these kinds of derivations before we move on? All right, what does this actually help us do? We'll come back and see exactly how this is done toward the end of the class. But for the moment, let's talk about parsing and membership and how this helps us to analyze strings in a language. So with grammars, we care to say, given some string, is that string in the language of the grammar? That is the same compiler's question as, given that we have a program, is that program written in the language that this compiler represents or recognizes? If we have a Java compiler, then a string that is a program, can that be broken down using the associated rules of the grammar? Now, can the grammar become this program? As an example of one such program that was written with the rules of the language. So this is a much simpler version of that on these toy languages, but that's exactly what kind of question we are aiming to answer by studying it in the first place. But now think about how we might actually be able to do that within the scope of, we have a grammar, we have a string. The question is this string producible by this grammar? If the grammar is ambiguous, this is going to be a very difficult question to answer. Because there's no one way to produce it. There may be a ton of ways to produce it, which means we need to do a full search through the entire search space of everything the grammar could produce. It's going to be intractable when we start blowing this problem up to real compilers, real programming languages, real programs. So one way to brute force this, if we hate ourselves, is to generate every possible leftmost derivation from the grammar and then just map them and say, did we produce the string? Did we produce the string? Did we produce the string with every single possible leftmost derivation that we could make from that grammar? So how would we actually do that? We start with the start non-terminal, and then we say within a single step, how many strings could we produce if we applied every single production? What are all of the ways that we would end up with terminal and only terminals that represent a string in the language within a single step? Then we would do it for 2 steps. Look at every possible place that we could get within 1 step, and then ask where could we get within 1 step of that? But you can see that this just creates a tree with a really large branching factor. So eventually we could start to prune this tree. Whenever we get something that is longer than the query, we know that we can't take away characters. So there's no reason to keep searching that space. So whenever we can't produce the query anymore, we just cleave off that or shave off that branch and then keep searching and keep searching and keep searching. Keep repeating. What's nice is if the string is in the language, then at some point we will find it, which is awesome. What's the downside?
Finite doesn't mean in your lifetime.
It definitely does not. It could take a very long time, but there's an even bigger problem. What if the string's not in the language? Does this process ever prove that the string is not in the language? We just haven't found it yet. And since this is an infinite language, we're just going to keep looking and keep looking and keep looking without any way to verify or validate that we can terminate and say the string's not in the language. So for the moment, we're going to call this procedure brute force parsing. And so, yes, brute force parsing is tedious. It's horribly inefficient because we are going through an exponential length process to even find things that are in the language. Without knowledge based on, we may never terminate. If the string is not in the grammar's language, we could be searching this forever, just saying we haven't found it yet. We haven't found it yet. These are the kinds of algorithmic processes that you will need to go through when designing solutions to your own problems out in industry. If something is either intractable or you're not guaranteed to find a solution, then you should intuitively be able to determine that as a reason why or why not to use a particular algorithm to solve a given problem. Being able to ask why does it have these issues? You can figure that out just by looking back on the grammar. And we have no way within context-free grammars to reduce the length of a string. If we've created 10 terminals so far and some non-terminals, the best case, all of those non-terminals go to lambda and we're left with the 10 terminals that we've generated so far. We have no way to take those 10 terminals and create a 9-terminal string or an 8-terminal string or a 7-terminal string. That's helpful because we get to cut off those branches once we produce a set of terminals that's longer than our associated string, but there's no guarantee there isn't some kind of loop in that process where we end up back where we started without producing any new terminals, which could create a process that goes on forever. Does that make sense to people? So some pretty poor qualities to brute force parsing. It's a bad idea to move forward with this. So the solution, or one possible solution to this, is to disallow productions of particular forms. As long as we can show in some way that whatever languages that we could represent before, we have a way to represent them after we disallow certain production types, then we'll be okay. So non-terminal arrow lambda is a problematic production type because it deals with the entire length of the string. We don't know how many terminals are going to be the end result of a string that is length 20 with some terminals and some non-terminals. There's no way to know that. But if there's no way for that non-terminal to produce 0 characters, it has to produce at least 1 terminal, then we have some way of knowing a floor for how long those strings are going to be. So something like, if we don't have a non-terminal arrow lambda and we start with an S arrow, capital A, capital B, capital C, what do we know right off the bat? String is at least 3 characters long. We can't make any of these non-terminals go to lambda. There's no way to just make them go away. So they're going to produce at least 1 terminal, as long as this leads to some path that can terminate. So now, based on the length of the string that we are producing, as we solve this, we have some hint as to how long, some floor as to how long the string is going to be. Now we can trim and cut off branches of the tree whenever the size of any of the characters becomes longer than the query string. Super useful. The next one is non-terminal arrow non-terminal, because that will create some kind of loop. I will state that neither of these restrictions affects what languages we can actually represent with this. Does anyone have any intuition for that? Why is that?
Because for grammars that use regular expressions, even like when we're using grammars like this, either right facing or left facing, it's common to have terminal points and to have looping parts of the problem. So this is relatively common no matter how you choose to signify regular expression.
Okay. What if it's not regular? So we're talking about the entirety of the context-free. So it's something that works for regular, or thinking of regular is great because it is a smaller piece of that pie. I think the second rule is a little bit easier to see here. Why can we get rid of all productions of that form? Somewhere in our grammar, we have something like B arrow C as a rule.
We could have just produced the C rather than producing B.
Yeah, so for instance, we have an A rule that is A arrow BC. And maybe there's some other rule, B arrow something. We can turn this now into A arrow. We can just back propagate and say CC or BC. And then this rule can go away because there is no other. If we had gone through that rule, we would have produced this instead of that. You just propagate that through the entire grammar, wherever this rule could be applied, you fork this, not arrows, or you fork it and create 2 different options at that point. So let's give you a slightly more complicated example. Something silly like this. So A has some other meaning associated with it, but now we can create additional meanings here in this S because it's the only place that this A is used on the right-hand side of a production. So we could say this is equivalent to now CB or C, as there is no C. Doesn't matter what this does, but we can now take this rule and make it go away. Because every way that this could have been applied now on the right-hand side of an expression now still can produce what the A used to produce, but can now also produce what the C can produce because A can be represented as just C. You have a direct way of whatever A was, it could have been C. But now there's no place where this could possibly be used that doesn't also have a definition for it, so it can go away. And you have an equivalent grammar. How about the non-terminal arrow lambda? Is there any idea for why that can go away within a particular grammar and represent the same language? A little bit harder to see, but it's kind of along that same path that wherever it shows up on the right-hand side of something, you could, at that point, make it go away or not, backpropagate, make it go away or not. So you could redesign the entire grammar without lambdas in them. So I'll let you in, it's possible, and let you play around with that if you're curious, but the final rule here is that we can create an equivalent grammar without these two kinds of rules. And if we do this without these two kinds of rules, the benefit that we get is that we can put a cap on the size of an associated string and a derivation that can produce the query string. So now we have a length of the possible number of derivations. So once we reach a particular depth, we can give up saying that we can't generate this, or we've already found it. The basic idea is if we would have been able to find it, we would have found it already. So if the string we're trying to say, if we don't allow these two rules and we're looking for a string like A, B, B, we know that by the time we hit depth 6 in this tree, we would have discovered it or not. Yeah.
So kind of understanding it a little bit, like, I can understand what we're gonna get into, but how could you represent a language that accepts the empty string without a lambda?
You would take an existing grammar and you would add a new rule to the top of it to be able to accept the empty string. So here is the existing grammar, and then you can factor that into something like, and now this is this language, except it accepts the empty string. So you basically say that it's the union of the empty string and this language that accepts everything that it does except for the empty string. It's kind of silly, but
So at that point, you just kind of have to break proportions.
yeah. But it means that we have a way of representing the rest of the language without that empty string, without the lambda. That is a really good point to catch and note that without that lambda, there is no other way to represent the empty string. So now we have a way of at least making brute force parsing complete. We have a way of answering no. If we reach twice the depth of the length of the string and we haven't found a solution yet via some depth first search, we cap the size of that depth first search at that level. Then if we enumerate every possible string within that depth, we can determine no. For the first time, no, this string is not in this language. However, there's still the other issue that it was tedious and inefficient. So what is the complexity of brute force parsing? Go back and show you this. Maybe that will help. So we start with, think of building this kind of like a parse tree. We can take this S and we can apply any of the associated productions that S can go to. Who knows how many of those are? We have to search that entire space. That entire space will produce one or more characters. It's either going to produce some non-terminals, but eventually those non-terminals have to produce terminals. So that branches out. Each of these branches out based on the number of productions that each of the associated non-terminals can produce in any of these. So whenever you have a for each at each level of depth in a tree, it's going to be exponential based on the branching factor of the size of that tree. Even though we have an associated cap to the depth, the fact that there is a branching factor to that says that it's going to be exponential. And what do we know about exponential time complexity algorithms?
They're no good.
They are bad. So yes, with every single leftmost derivation, we end up multiplying the number of potential derivations by the number of productions in the grammar that could be applied at that stage, which is worst case, the entire sequence of productions in the grammar. And we do that at each level for each of the associated branches. So at most 2 times the length of the string repetitions of that process. So we end up with exponential p to the 2 times the length of the string, worst case complexity. So conclusion is grows exponentially with respect to the length of the string. The very big summary is just gross. This is intractable. It's not something that's going to scale for very long strings, and programs are just very long strings, right? So being able to map with the associated large branching factor of something like a programming language's grammar with the length of a program is going to create an exponentially complex process that becomes worse and worse and worse as the program gets longer. That seems like it's going to be very difficult to implement in a way that when we run a compiler on a program, we want to know the answer, to have an executable to run within our lifetimes. And if we utilize something like this for long programs, it's going to take a very long time to compile. So using any kind of compiler that you've used before, what's the longest you've had to wait for a program's compilation? 2 seconds at most. You
Not long
run
enough for me to worry about it.
GCC or G++ or build and run, had to wait half an hour for something. That is possible versus it's complicated.
Yeah, it was a big.
Yeah.
The machine learning class, that was like,
Oh, is that for just training? Because you're doing an algorithm while you're going,
yeah,
while you're training. So that's not technically compilation, but it is pre-processing.
yeah, but I meant, like, there was at one point where just because there's such a huge, like matrix, something like that, in order to compile it to like a minute, something like that. I was like, oh, that's the longest, but
Yeah.
I don't know why.
Yeah. So you can't imagine, or it's easy to imagine that we're not using brute force parsing in any compilation system that we use. So we absolutely need a method that is more efficient than this. And we'll actually go into the exact methods that are used for this problem and why. The best you can do in general is a cubic method. And in certain examples, you can actually get all the way down to linear. And we'll talk about both of those by the end of the class. So we'll return to the problem in a bit. Yeah, linear time methods exist for restricted but important special cases. Last thing we'll cover for the day is the concept of a simple grammar. So now we have, and this is going to be true throughout the course, lots of different names for lots of different classes of things. So a regular grammar, you might get confused with a simple grammar because regular languages are simpler in some sense than context-free languages, but that's going to lead you astray because simple grammars represent types of context-free grammars. So a grammar is simple if all productions adhere to a form where we have a single non-terminal arrow, a single terminal followed by 0 or more non-terminals. And then the associated pair of non-terminal to terminal appears at most once within that grammar. So those are the two rules getting us to the concept of a simple grammar. Take a second, see if you can figure out exactly what that means or why we might care about that class of language. And we will ask whether this grammar is simple. What do we think? Yes or no? We have one vote for yes. We have one vote for no. 2 votes for yes, 1 vote for no. Anyone else with an opinion? Is that no, I don't have an opinion, or yes, I have an opinion, and the answer is no?
Yes, the answer is no.
Interesting. So now we're split 2 and 2. So each production must be of the form non-terminal arrow terminal. So we need a terminal at the leftmost position followed by 0 or more non-terminals. So each one of those that has 0 non-terminals, 1 non-terminal, and 2 non-terminals on that right-hand side. This production goes S arrow A stuff. This one goes S arrow B stuff. This one goes S arrow C stuff. So it adheres to both of these rules for those reasons. If we see an A and the current non-terminal is an S, we know exactly which production to apply. So this is a simple grammar. Real quick, let's take a look at this one. Is this simple? No, we have 2 productions that go S arrow A something. And because of that, if we see the next character is an A, and we're currently at the non-terminal S somewhere in that, then we don't know which production to apply. It is a branch. So basically what we are saying with simple grammars is that we don't allow branching. This one is not. And we can also describe many features of programming languages with concepts like simple grammars. So it's useful to be able to represent them. So we will stop here and come back to it tomorrow. We're going to start getting into the fun nitty-gritty of context-free grammars. They get much more fun. So we'll do that tomorrow. Question?
I have a question.
Yeah.